Hello all, welcome to the hands-on series on Fundamentals of Generative AI and Large Language Models, Theory and Practice. In today's session, we'll be demonstrating the use of convolutional neural network in order to predict and classify the images. So let us go through the hands-on. Convolutional neural network makes use of the fundamental operation called as convolution, which is multiplication of numbers and then summation of the numbers. So this acts as the base for the convolutional neural networks, followed by some pooling operations, use of activation functions, and finally the prediction will be done on the images. So let us go through the hands-on. So the first part, as usual, is importing the necessary libraries. So we are importing the TensorFlow as a TF. TensorFlow is a deep learning framework which is used to build the neural networks. So this is required in order to have the neural networks. Then from TensorFlow Keras package, we are importing the datasets, layers as well as models. So dataset is required because we may sometimes use ready datasets which are available in Kaggle or maybe UCI repository. So in our implementation or today's hands-on, we are making use of the CIFAR 10 dataset, which is a Canadian Institute for Advanced Research dataset, which comprises of 10 different classes of data, that is automobile data, vehicle data, as well as animals and the birds data. So we are importing such data sets which are available in Google or Kaggle, and then importing the necessary layers. So as we all know, neural network comprises of 3 different layers, that is the input layer, the dense layer and the output layer. So in order to have the different set of layers, we need to import the layers, and then to build the convolutional neural network, we also need to import the model function. We also import the matplotlib.pyplot as PLT. So matplotlib.pyplot is a data visualization package which is required for visualizing the data. And then we import the numerical Python, that is NumPy as NP. So as the name suggests, in order to deal with arrays or numbers, we need this NumPy package. And from sklearn, which is scikit-learn, from the metrics sub-package, we import confusion matrix as well as confusion matrix display. So from scikit-learn metrics, we can have different metrics in order to measure the performance of the deep learning models or maybe the machine learning models. So out of those metrics, we are choosing the confusion matrix or the confusion matrix display, which is used to give a comparison between the true label and the predicted label. So we have the actual truth or the ground truth for every class that is present in the data set. That is for the training data set. Similarly for the test data set. Now whatever model predicts, when we compare that predicted output with the true output, we need to display that number or we need to display that particular output. So in order to have that display, we need this confusion matrix display. So this is all about importing the necessary libraries. Now coming to loading the data set. So as mentioned earlier, we are using the Canadian Institute for Advanced Research dataset, which comprises of 10 different classes of data, mainly the vehicle data, the animal and the bird data. So they have 10 classes, namely the aeroplanes, the automobiles, birds, cats, deer, dog, frog, horse, ship and the truck. So these are the 10 different classes present in the dataset. So what we do in the first line in the second code cell is that CIFAR 10 dataset we are loading into various variables called as training set and the test set. So we have 4 different variables, namely the xtrain, ytrain as well as xtest and the ytest. So training data comprises of the input data. So that input data comes under xtrain. Training data will also have the output data which comes under ytrain. And then the test set will have the input data which can be called together in xtest, and it will have the ground truth or the actual label or the actual output which can be called as ytest. So this ytest is something which has to be compared with y prediction. So that is why earlier we have imported the confusion matrix. So now we are having 4 different variables in which we have the training set and the test set. Now coming to training data and the test data. So we know that whatever data set we have considered, this is a set of images. And when we talk about the grayscale image or the RGB or the color images, they will have values from 0 to 255 because they have 256 different levels or 256 different intensity values which vary from 0 to 255. So when we consider this 256 different values, it is always difficult for the model to train such data or to learn such patterns or to learn those many intensity or the pixel values. So in order to make the learning easier, what we do is we try to normalize the data. So all such values which are varying from the range 0 to 255, we are putting in a range of 0 to 1. So we have the highest value as 255. That's why we divide the training set as well as test set by 255. The maximum value is 255. So let us go through one example. See, we take one RGB or a color image which has 3 channels, the red, the green and the blue channel. So here red values can lie between the pixel intensity 0 to 255. Similarly, this also varies from 0 to 255 as well as blue varies from 0 to 255. So total values are 256 here as well as 256 and 256. The model learning becomes very tedious whenever we try to deal with these many numbers. So what we do is, since the maximum value is 255 here, any intensity that we come across in the image, say I take a 4x4 image, say the pixel value is 100, maybe 50, this is 10 and this is 250, all values lying between 0 to 255. So I divide each of this value 100 by 255, similarly 50 by 255. Likewise, if we have this value as 255, then that value is 255 by 255. See, if we have the minimum value as 0, so that value also to be divided by 0 by 255. So what happens is, in this case the value remains 0. When we divide 255 by the maximum value which is 255, the value is 1. So now we have the normalized pixel values in the range 0. We have the normalized pixel values in the range 0 to 1. So this is the importance of normalization. Now coming to the different class names, as I mentioned earlier, there are 10 different classes: aeroplane, automobile, bird, cat, deer, dog, frog, horse, ship and the truck. So these are the 10 different classes present in the CIFAR 10 dataset. So let us now print the number of samples present in the training set as well as the test set. So print statement, and the print statement is training data shape and test data shape, and the function used is the shape function on the training set as well as the test set. So once this is run, we are able to see the output training data shape and the test data shape. So there are 50,000 images or 50,000 samples in the training set and 10,000 samples in the test set. And when we look into the shape, what happens is we have each image which has 32 pixels as width, 32 pixels as height, and there are 3 different channels, that is R, G and B. Same thing in case of test data shape, that is 10,000 samples we have in the test data set, 32 pixels as width, 32 pixels as height and 3 different channels. So this is all about displaying the data shape, both the training as well as the test data. Now let us display some of the sample images. So for displaying or for visualization, we need this matplotlib library. So from PLT, we have the figure function. Within the figure function, we are making use of the argument called as fig size. Let us have a figure of 10 inches in width and 5 inches in height. So these two numbers represent the width and the height of the display or the figure. So for I values varying in the range 10. So when we write a range of 10, there are 10 different values and the index value varies from 0 to 9. So likewise, I am trying to display 10 different images varying from 0 to 9. Let me make use of the subplot function. Let the subplot function have 2 rows and 5 different columns. So 2 rows and 5 different columns will help us to accommodate 10 different images, and let the iteration vary from 0, like 0 plus 1 becomes 1, then 1 plus 1 becomes 2. Likewise, we go up to the last image. So I plus 1 number of times. And then let me show the training samples. So X train for every iteration that I am going through, or for every index that is varying from 0 to 9. Let the title of this image be the class names, that is the corresponding class names or the 10 different class names which we have already seen. And the class names are available in the Y train, because Y represents the labels or the target names which is given for the X train. So let me display those class names for every index 0 to 9. And plt.axis off. Axis is off because we need not represent anything in the x-axis and the y-axis. We need not give any name for the x-axis and the y-axis. That's why we keep the axis as off. So let us display this particular figure. So when we try to display this figure, we see the figure as displayed in 2 different rows and 5 different columns. Put together, there are 10 different images. So we are able to see images of frog, truck. There are 2 trucks which are displayed. Then we have image of a deer, automobile, one more automobile, bird, horse, ship and the cat. So we have seen some of the sample images. Now coming to the major part, that is building the convolutional neural network. So as mentioned earlier, convolution becomes the fundamental operation under convolutional neural network. So we try to build these models, the sequential models, because we stack layers one after the other. So we need this happening in the sequential manner. So let us have the first convolutional block. So let me add the layers, that is layers, convolutional layer. The first convolutional layer having the number of filters as 32. Let the kernel size be 3, 3, that is 3 cross 3. Activation function used is ReLU activation function, and the input shape as defined earlier, 32 cross 32 cross 3. And then after this convolutional layer, we add the max pooling layer of the filter size 2 cross 2. Now let me come to the second convolutional block. Once again add the layers, convolutional layers of 64 different filters. 3 cross 3 is the filter size, and then the activation function is ReLU, followed by the max pooling layer once again of the size 2 cross 2. Now coming to the third convolutional block with the 128 number of filters. 3 cross 3 is the filter size and the activation function is once again ReLU. So we are having 3 different convolutional layers one after the other. So we are always free to use the number of convolutional layers as per the requirement, as per the data set, or as per the size of the data set, as per the execution or the computation time that is really available, or maybe the memory which is available. So in our case, we are using 3 different convolutional layers back to back. But always we should remember, a basic CNN can always have one convolutional layer followed by the max pooling layer with some activation functions, and immediately come to the dense layer. So that is the flattened layer. So once we have these 3 different convolutional layers, we have the flattened layers which will help in converting the matrix into an array. So we can see this flatten function which will convert that 2D array or a 3D array into 1D array. And then coming to the fully connected layer, which is the output layer in our case. So output layer which is obtained by calling the dense function. Let us have 128 such neurons, and the activation function is ReLU. After this dense layer, let us use the dropout function to drop the functioning of certain neurons, or to drop the functioning of some of the hidden neurons. So what we are trying to do is, we are trying to reduce the 50% of the neurons in order to generalize the model, or in order to have a regularized model, so that we can avoid the overfitting condition. And at the final output layer, we have the dense function once again. since there are 10 classes present in the data set, this number of neurons should be always equal to 10. Say if we have 2 classes, then the number of neurons will be equal to 2. So we should always remember that the number of classes will define the number of neurons in the dense layer. And finally, we have the activation function, which is the softmax activation function. So now let us go through step by step what exactly is happening in each of the layers. What is the importance of this convolution, the importance of max pooling, similarly importance of the dense or the flattened layer and the dropouts with an example. So let us consider an image, maybe a 5 cross 5 image. Instead of taking a very heavy image of 32 cross 32 as given in the CIFAR data set, I'll be taking a 5 cross 5 data set. So this is a 5 cross 5 data or a 5 cross 5 image which is taken for simplicity. So as mentioned earlier, this is a RGB image having 3 different channels. So one of the channel could be R, the second channel could be green and the third channel could be blue. So let me show the experiment on the red channel. And the values are varying from 0 to 255. So let the first value be 10, then 2, 1, 0, 2. So these values represent the pixel intensity. So this is 5 cross 5 image, and when it is RGB, there are 3 different channels. Now coming to the first convolution functions. Convolution are those layers which will help in getting the feature extraction. That is, an image can consist of various points, it can consist of various shape, textures, maybe edges, lines. So all these are the different features which have to be extracted. With the help of these features, what happens is, as we go deeper in the network, as we go deeper in the layers, feature extraction becomes more tedious. The filtering becomes more tedious. Unlike the first few layers, number of filters used are very less. We can see it here. The number of filters used in the first convolution layer is only 32. Then coming to the second convolutional block, the number of filters used are 64. When coming to the third convolutional block, the number of filters used are 128. So this is all about feature extraction. With the help of different features or with the help of different filters or the mask, we are going to extract the features. So at the first layer, it is the basic information which has been extracted. At the second layer, maybe a little higher, and when coming to the third block or the third convolutional block, the filtering will be more tedious. So this helps in extraction of the various features present in the data. So coming to the convolution. So convolution makes use of different kernels. So if I am talking about extraction of edges, initially the extraction of edges can be extracted using some of the operators like Previtt operator, Sobel operator or Canny detector and so on. So let me take an example of Previtt operator. If I am going to make use of Previtt operator and I want to detect the vertical edges, then a 3 cross 3 filter would be having a mask of this way. If I am talking about the Previtt operator and the horizontal mask, then this is the mask which is to be used. Similarly, if we are going to use the Sobel operator, this will be 1 to 1 and this is vertical in nature. If I am talking about Sobel horizontal, then this will be -1, -2, -1, 0, 0, 0, 1, 2 and 1. So any of these operators could be used. So basically overlapping this particular mask on the given image. So when I try to overlap this particular mask, say for example the vertical pivot on this, I need to superimpose on the given image. So nothing but I have to do the pixel multiplication. So 10 into minus 1, which is minus 10, 2 into 0, which is 0, plus 1 into 1, which is 1, 2 into minus 1, which is minus 2, 5 into 0, which is 0, 4 into 1, which is 4, plus 0 into minus 1, which is 0, 0 into 0, which is 0, and 4 into 1, which is 4. So I need to add all these values. So minus 10 plus 1, minus 9, minus 11, this is 7, and this leads to 11. So this is the value which I get after convolution. So what I need to do is, this particular mask I need to superimpose at every edge this way. I superimpose on this area, next I superimpose on the third area by making use of windowing technique, or by making use of a parameter called as stride. So in my case, if I am using a stride value of 1, then immediately I need to superimpose this mask on the image such that the overlapped pixels are 210, 542, 044. Again, once again, if I am using a stride value as 1, then my next window will be comprising of value 102, 423, 443. Like this, I will superimpose this mask on every pixel that is present on the given data. So what is happening here is, we are getting the convoluted output, which is nothing but the feature map. And when we look into the output or the feature map, the size will be reduced when compared to the initial input. So we see here it is a 5 cross 5 cross 3 image. So this 5 will be reduced. So how do we find this reduced value is, say output width, the width of the output image will be equal to the width of the input image minus the filter size plus 2 times padding divided by the stride plus 1. So width of the input image, is 5 in our case, 5 minus the filter size is 3 cross 3. So the filter width is 3 plus 2 times padding. Padding is using of zeros in order to maintain the edges. If I am trying to have zeros throughout, in the boundaries this way, and do perform the convolution, then what happens is I am trying to preserve the edges of the image. So in case I am using padding, then accordingly how many values of padding I will be using, how many rows or columns of padding I am using, based on that padding value will be written here. So in my case, whatever example I have taken, zeros are not used. So therefore 2 into 0, which will be equal to 0, and as I mentioned earlier, the stride value will be equal to 1 plus 1. So 5 minus 3, which is 2 divided by 1 plus 1, which is equal to 3. So after performing the convolution on the given input image, which is of the size 5 cross 5 cross 3, I will be getting the output feature map of the size 3 cross 3 cross 3. So this refers to the width, this refers to height, and this refers to the number of channels. Same thing, same computation to be performed even in case of height. So what happens in case of height is, this 5 is to be used. This particular 5 is to be used. So W out will be W out for height. This is W out for width. So this is height, input height minus filter plus 2 times padding divided by stride plus 1. So even in this case, it is 5 minus 3 plus 0 divided by 1 plus 1, which happens to be 3. So that's why this is written as 3. So the original input is reduced to a final size of 3 cross 3 cross 3. So what is the benefit of having this? It is memory efficient, as well as the computational time will be very less. So this is the benefit of having the convolution, as well as it will help in extraction of certain features. So as mentioned earlier, here we are using the Prevet operator. So it will help in detection of the vertical edges. Suppose I am using the horizontal operator, then it will help in detection of the horizontal edges. Similarly, in case of Sobel or Prevet, whichever operator we are using, vertical or horizontal, based on that we will be able to preserve or detect those edges. So this is the convolution operation. So now after the convolution, we are left out with 3 cross 3 cross 3. So now let us see what is spooling here. So now I am left out with the 3 cross 3 cross 3 image. This width is 3, height is 3 and number of channels are 3 here. This refers to the channels, width and then the height. Say for example, after convolution, I am getting the value. This value was anyways 11. We had calculated it. After certain calculation, we get to know the values are this way. -3, 1 and -1. After calculation, we would getting the value this way. Then what is to be done is, we have this pooling. We have this pooling operation. So what is happening in pooling is, we are making use of the maximum pooling. So this pooling operation once again helps in reducing the computation time, or it is a memory efficient operation. So the pooling could be sometimes the average pooling or minimum pooling. For simplicity, we have used maximum pooling, which helps in detecting the features which are very much important when compared to the other. So for pooling also, we need to define the filter size. Since it is a 3 cross 3 image, I can take blocks of 2 cross 2 size or 1 cross 1. So let me take the size as 2 cross 2. So what is the maximum value here out of this? It is 11502. The maximum value is 11. Now this next stride, I have the values 5021. So the highest value is 5. In the next window, I have 0, 2, -1 and 1. So the maximum value is 2 here. And then the last window, it is 2, 1, 1 and -1. The maximum value is 2. So this is the max pooling operation. We get to have only the maximum values. So once again, the 3 cross 3 cross 3 image is now converted to 2 cross 2 cross. This is done for every channel. So this 3 remains the same here. So what is the formula? Suppose I am talking about the width, then width of the pooling operation will be width of the input image minus the filters. There is no necessity of padding here, because we are not extracting any edges, or we are not doing any operation on the edges. Instead, we are considering 4 values at a time, or maybe 10 values based on the filter size. So padding is not at all necessary here, divided by stride plus 1. So in our case, the width was 3 minus, we have taken 2 cross 2 filter size. So width will be 2 divided by stride was always 1 plus 1. So this will be equal to 2. Similarly, output of the height will be the input height minus the filter divided by stride plus 1. So once again, this height is 3, 3 minus 2 by 1 plus 1, this remains as 2. So that's why we get the width as 2 as well as the height as 2, and channel remains the same. Now on this, if we are performing the ReLU operation, which is an activation function, there are several activation functions that can be used. For simplicity, once again based on certain advantages, we make use of the ReLU function. So ReLU, the functioning of ReLU is such a way that it is maximum value of 0, whatever input we have. So if I compare this image, the pooled image, so 0, 11, I am left out with 11. 0, 5, maximum value is 5. 0, 2, it is 2. 0, 2, it is 2. What if we had a negative value? Say for example, if the obtained pooled image was 11, -5, 2 and 2, then what happens when we do max of 0, -5 is, we are getting the value as 0. So after the activation function, we will be able to get some non-linearity in the data. That is, even negative values will become positive. So, it is a one way of adding non-linearity to the data. So, this is all about the ReLU. So, we have covered the convolution, we have covered the max pooling. So, finally, what happens in this flattened layer is, so let me go back to the same example. After ReLU, I have these 4 values which are to be converted into 1D array. So, 11, 5, 2 and 2. These are now my inputs. I can be calling them as the 4 different features which are extracted from the image. So, x1, x2, x3 and then x4. So, these are the different values. To these values, when we multiply the associated weights and then the bias, we get the final output. Those final output are nothing but the raw scores which will be converted into probabilities by making use of the softmax layer. So, let us see even that. So, from the example, we had the inputs as 11, 5, 2 and 2 which were x1, x2, x3 and x4. These were the inputs. This has to be multiplied by the weights. So, the weights, the number of weights or the matrix weight matrix will be based on the number of inputs that we have. So, what happens is weight will be equal to W1, W2, W3 and W4. It is based on the number of inputs that we have, and the number of columns depends on how many neurons we want in the hidden layers. Say for example, if I want only two different neurons, then this will be W, this will be 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 2, 4, 1 and 4, 2. So, if I am trying to draw the network, then at the input side, I have x1, x2, x3 and then x4. In the hidden layer, we have 2 neurons. That is why we have 2 different columns, and then at the output layer, we have 10 different neurons, because we should be having 10 different neurons here, because we have 10 different classes. So, the relation is the final output Z will be equal to W transpose. We have this W, we have to take the transpose of this into the input plus the bias. So, in our case, since there are 2 neurons in the hidden layers, bias will be having 2 values B1 and B2. So, this Z will be giving us raw scores. They are not at the probability. So, how do we convert this into probability is by using the softmax layer. So, softmax layer will take the 10 different values. Suppose I take an example of 10 different values as say 0.5, 0.15, 0.2, 0.1, 0.01. I take 10 different values. How do I get the probability? This is no more a probability, because when we sum up these values are not equal to 1. So, how do I get the probability is e power 0.5 divided by e power 0.5 plus e power 0.15 plus e power 0.2, so on up to we need to take the exponential of all the 10 different values. So, now whatever answer we get, that is the associated probability. So, that is the probability of a class for the index 0. Similarly, if I want the probability of the class being 1, if I am taking that, then that will be e power 0.15 divided by all the exponential values. So, likewise, I will be getting the probability for each of the 10 different classes. So, whichever probability is high, the model is going to predict that particular class. So, this is all about building the CNN model. Now, quickly we will go through compilation or configuring the model as well as training the model. So while configuring, we need to take some optimizers. So in our case, we are taking the Adam optimizer, and the loss is a sparse categorical cross entropy. The loss could be either binary cross entropy or categorical cross entropy, or sometimes the sparse categorical cross entropy. When we use binary cross entropy is when we have only 2 classes. Since we have 10 different classes, we are left with the option either for using the categorical cross entropy or sparse. But in our case, we have used the sparse categorical cross entropy because all the 10 different classes what we have, they are mapped to 10 different integers. Maybe automobile is mapped to value 0, truck may be mapped to value as 1, bird may be 2. So we have 10 different integers. So whenever we come across integers, we need to use the sparse CC as the loss function. Now let the metrics that we are going to measure be accuracy. So let us measure both the training as well as the test or the validation accuracy. So that's why the metrics is accuracy. Now coming to training of the model. So model which is fit on the training data, X train and Y train. Let the number of epochs, number of times the model has to go through the data is 10 number of times. Let the batch size be equal to 64. So what is this batch size is? So the first 64 samples, 0 to 63 image. For this, the model will do the prediction, it will calculate the accuracy, it will calculate the loss, also it will calculate the weights. Then it will back propagate the weights. So weight updation takes place at every 64 samples. Now coming to 64 up to the next 64 samples, 64 to 127. Similarly, prediction happens here, accuracy will be measured, loss will also be measured, and then the weights also be updated. So this refers to the batch, how we are separating or how we are grouping different samples into batches. So likewise, we have 64. Let us consider 64 different batches. Now let the validation split. Let us divide this training data into 80% as training and 20% as the validation set. So that's why the ratio is 0.2, validation set as 0.2. And verbose equal to 1 means let us display the result of every epoch in one line. That's why we have 1. If we make it 0, there is no displaying of the progress bar. If we make verbose equal to 2, then it will be displayed in 2 different lines. So we have 10 different epochs. For 10 different epochs, we have the accuracy and the loss, which is pertaining to the training one. We have accuracy as well as loss, which is pertaining to the validation set. So as we progress in our epochs, the final accuracy what we come across is 72%. So validation set has got an accuracy of 72%, and training accuracy is 75%. So we see that there is no overfitting condition here. Now coming to the plotting of the accuracy as well as the loss. So as mentioned earlier, figure function is used for plotting with figure size as argument of 12 inches in width and 5 inches in height. So accuracy, let us plot this accuracy. Subplot 1, 2, 1. So 1 row, 2 columns, and in the first position, let us have the accuracy plotting. Similarly, subplot 1 row, 2 columns, and in the second location, let us plot this loss. So we want to plot the training accuracy as well as validation accuracy. Let us give the label as training and validation. Let the title be model accuracy. Let us give some label both on the x-axis as well as the y-axis. So x label is epoch and y label is accuracy. Same thing to do with loss. Labels are training and validation for the training loss and the validation loss. Title is model loss, x label and y label as epoch and loss. And let us have the legend. So legend is this kind of display. So which color holds good for which one? So training represented in blue color, validation represented in orange color. So this portion refers to the legend. So let us show this particular figure. So we see that the model accuracy increases as the number of epochs increases. So we are able to see a display of epochs versus accuracy, similarly epochs versus loss. So for 10 different epochs, we have the accuracy as well as the loss. We see that the accuracy is increasing both for the training as well as the test set. As seen earlier, the validation accuracy is slightly less, that is it is nearly equal to 72%, whereas the training accuracy was 75%. Same thing to do with the loss. Loss was slightly higher for the validation set, even though it is decreasing for every epoch. Now finally coming to the evaluation on the test set. We also have a test set which comprises of 10,000 different samples. So we have this test loss and test accuracy which has to be evaluated on the test data. Now our test data comprises of two different variables, X test and the Y test. So let us display both the testing accuracy and the testing loss. So test accuracy is 71% and the test loss is 0.82. Coming to the prediction, let us see how the true label and the predicted label really works. So let us see the prediction part. Let the built model predict the X test value. Let it be saved in a variable called as predictions. So now let us do such predictions for 5 different samples. So for I in the range 5, 0 to 4 is the index, totally 5 different samples. Predicted label is a variable which I take, and let us show the prediction, or the prediction is done for which the probability is very much maximum. So we have already seen how to get the probability. So for each of the 10 different classes or the raw score which is available after this particular transformation from the 3 channel to the 1D array, whatever we have seen here, we have 10 different probabilities. Whichever argument gets the highest probability, that corresponds to a class, a proper class. So let us take the argument of the maximum prediction or the maximum probability, and let it be saved as predicted label. And we always have this actual label which is got from the Y test, which is the actual label which is present for the test data set. So let us plot it as a figure. So figure is a function which is used. Let us show that figure, X test figure. Let the title be prediction and the actual. There need not be any axis, x-axis or y-axis labeling. That's why we need to off it, and let us show the figures. So what has happened here, this for the 0th argument. So prediction 1 is cat, for the actual data which is cat. So that can be seen here. Similarly, we can see the shape of the ship here. Actual one is ship, predicted one is also ship. Similarly, once again we can see the actual one is ship, the predicted one is also ship. Even the 4th sample, the prediction and the actual are the same. Even for the 5th one, the prediction and the actual are the same. But it need not be same for all the test samples which is present. So now let us display through a confusion matrix how many misclassifications and how many correct classifications have taken place. So with the help of confusion matrix, we are going to display. So let us have the probability which is obtained by the largest index or the largest argument or the largest value present. So on the predictions, and let those be present on the axis equal to 1. So axis is equal to 1 refers to columns. So all the predicted labels, let it be on the y-axis, that is this way. This is the predicted ones on the columns. So by default what happens? The true labels comes on the rows. It will be by default coming on axis is equal to 0. So let the true labels be got from the Y test, which is the flattened layer. Flattened refers to 1D array as mentioned earlier. So let us compute the confusion matrix on the true label as well as the predicted label, and let us store it in a variable called as CM, and let us display the confusion matrix. So confusion matrix display, confusion matrix which is stored in a variable called as CM. Let us display all the class names, the corresponding class names. So let us have a plot. Let the color map be blue. We can have different colors here. Let us now have the hues of different colors of blue or different hues of blue. And X tick rotation equal to 45 here refers to this kind of rotation. If we try to maintain the 0 degree, what happens is these labels will overlap. So this is all the way of beautifying the display. So let us have this title as CNN CIFAR 10 confusion matrix. So let us show this confusion matrix. So as mentioned earlier, on the rows of the confusion matrix, we have the true label. On the columns, that is axis is equal to 1, we have the predicted label. So this is a 10 cross 10 matrix because we have 10 different classes. Obviously, number of classes will give us the rows and the columns of a confusion matrix. So this is a 10 cross 10 matrix, and on the diagonal, whatever numbers we see, those are the correct classifications done by the model. So true label was aeroplane and model has predicted aeroplane. We have 815 such instances or such samples. True label is automobile and predicted label is also automobile. So we have 839 such samples. So all these are the correct classification, and whatever non-diagonal elements we have, those are the false classifications done by the model. So if I take this example of 35, what has happened is true label which was present in the data set was automobile, but the model has falsely predicted as aeroplane. So likewise we have 35 such instances. Now if I take this example 16, so true label was automobile, but the model has falsely predicted it as frog. So likewise I have 16 such examples. So this is the confusion matrix on a CIFAR 10 data set. So the color map, whatever color map we see here, hues of blue, the lower numbers are indicated using the light blue shade, and as we go to the higher number, highest integer, those are represented using the dark blue color. So with the help of the confusion matrix, it is very much evident that most of the classifications are right, which is very much seen on the diagonal. And the non-diagonal elements, here and there are few misclassifications. That is why we have got only 72% accuracy. So with the help of this particular experiment, we have seen the implementation of convolutional neural network, which is on a CIFAR 10 dataset, which is Canadian Institute for Advanced Research dataset, having 10 different classes, mainly the classes comprising of vehicles, animals and birds. We have seen how to build a customized CNN model, unlike our basic CNN, which has one layer of convolution, one layer of pooling, and maybe certain activation functions, and then the dense layer. But what we have tried to do is, we have tried to have 3 different convolution layers having max pooling, after which we had the dense layer. So adding more convolution helps in more feature extraction, and with the help of features which are more important, prediction becomes very much easier. In this hands-on, we have seen the implementation of convolutional neural network. Thank you.